External ballistics or exterior ballistics is the part of ballistics that deals with the behavior of a projectile in flight. The projectile may be powered or unpowered, guided or unguided, spin or fin stabilized, flying through an atmosphere or in the vacuum of space, but most certainly flying under the influence of a gravitational field. Gun-launched projectiles may be unpowered, deriving all their velocity from the propellant's ignition until the projectile exits the gun barrel. However, exterior ballistics analysis also deals with the trajectories of rocket-assisted gun-launched projectiles and gun-launched rockets, and rockets that acquire all their trajectory velocity from the interior ballistics of their onboard propulsion system, either a rocket motor or air-breathing engine, both during their boost phase and after motor burnout. External ballistics is also concerned with the free flight of other projectiles, such as balls, arrows, etc. Forces acting on the projectile. When in flight, the main or major forces acting on the projectile are gravity, drag, and if present, wind, if in powered flight, thrust, and if guided, the forces imparted by the control surfaces. In small arms external ballistics applications, gravity imparts a downward acceleration on the projectile, causing it to drop from the line of sight. Drag, or the air resistance, decelerates the projectile with a force proportional to the square of the velocity. Wind makes the projectile deviate from its trajectory. During flight, gravity, drag, and wind have a major impact on the path of the projectile, and must be accounted for when predicting how the projectile will travel. For medium to longer ranges and flight times, besides gravity, air resistance and wind, several intermediate or meso variables described in the external factors paragraph have to be taken into account for small arms. Meso variables can become significant for firearms users that have to deal with angled shot scenarios or extended ranges, but are seldom relevant at common hunting and target shooting distances. For long to very long small arms target ranges and flight times, minor effects and forces such as the ones described in the long-range factors paragraph become important and have to be taken into account. The practical effects of these minor variables are generally irrelevant for most firearms users, since normal group scatter at short and medium ranges prevails over the influence these effects exert on projectile trajectories. At extremely long ranges, artillery must fire projectiles along trajectories that are not even approximately straight, they are closer to parabolic, although air resistance affects this. Extreme long-range projectiles are subject to significant deflections, depending on circumstances, from the line toward the target, and all external factors and long-range factors must be taken into account when aiming. In supergun artillery cases, like the Paris gun, very subtle relativistic effects that are not covered in this article can further refine aiming solutions. In the case of ballistic missiles, the altitudes involved have a significant effect as well, with part of the flight taking place in a near vacuum well above a rotating Earth, steadily moving the target from where it was at launch time. Stabilizing non-spherical projectiles during flight. Two methods can be employed to stabilize non-spherical projectiles during flight. Projectiles like arrows or arrow-like sabots such as the M829 armor-piercing, fin-stabilized, discarding sabot, APFSTs, achieve stability by forcing their center of pressure, CP, behind their center of mass, CM, with tail surfaces. The CP behind the CM condition yields stable projectile flight, meaning the projectile will not overturn during flight through the atmosphere due to aerodynamic forces. Projectiles like small arms bullets and artillery shells must deal with their CP being in front of their CM, which destabilizes these projectiles during flight. To stabilize such projectiles, the projectile is spun around its longitudinal, leading to trailing, axis. The spinning mass creates gyroscopic forces that keep the bullet's length axis resistant to the destabilizing overturning torque of the CP being in front of the CM. Main effects in external ballistics. Projectile/bullet drop and projectile path. The effect of gravity on a projectile in flight is often referred to as projectile drop or bullet drop. It is important to understand the effect of gravity when zeroing the sighting components of a gun. To plan for projectile drop and compensate properly, one must understand parabolic-shaped trajectories. Projectile/bullet drop. In order for a projectile to impact any distant target, the barrel must be inclined to a positive elevation angle relative to the target. This is due to the fact that the projectile will begin to respond to the effects of gravity the instant it is free from the mechanical constraints of the bore. The imaginary line down the center axis of the bore and out to infinity is called the line of departure and is the line on which the projectile leaves the barrel. Due to the effects of gravity, a projectile can never impact a target higher than the line of departure. When a positively inclined projectile travels downrange, it arcs below the line of departure as it is being deflected off its initial path by gravity. Projectile/bullet drop is defined as the vertical distance of the projectile below the line of departure from the bore. Even when the line of departure is tilted upward or downward, projectile drop is still defined as the distance between the bullet and the line of departure at any point along the trajectory. Projectile drop does not describe the actual trajectory of the projectile. Knowledge of projectile drop, however, is useful when conducting a direct comparison of two different projectiles regarding the shape of their trajectories, comparing the effects of variables such as velocity and drag behavior. Projectile/bullet path. For hitting a distant target, an appropriate positive elevation angle is required that is achieved by angling the line of sight from the shooter's eye through the center line of the sighting system downward toward the line of departure. This can be accomplished by simply adjusting the sights down mechanically, or by securing the entire sighting system to a sloped mounting having a known downward slope, or by a combination of both. This procedure has the effect of elevating the muzzle when the barrel must be subsequently raised to align the sights with the target. A projectile leaving a muzzle at a given elevation angle follows a ballistic trajectory whose characteristics are dependent upon various factors such as muzzle velocity, gravity, and aerodynamic drag. This ballistic trajectory is referred to as the bullet path. If the projectile is spin stabilized, aerodynamic forces will also predictably arc the trajectory slightly to the right, if the rifling employs right-hand twist. Some barrels are cut with left-hand twist, and the bullet will arc to the left, as a result. Therefore, to compensate for this path deviation, the sights also have to be adjusted left or right, respectively. A constant wind also predictably affects the bullet path, pushing it slightly left or right, and a little bit more up and down, depending on the wind direction. The magnitude of these deviations are also affected by whether the bullet is on the upward or downward slope of the trajectory, due to a phenomenon called yaw of repose, where a spinning bullet tends to steadily and predictably align slightly off-center from its point mass trajectory. Nevertheless, each of these trajectory perturbations are predictable once the projectile aerodynamic coefficients are established, through a combination of detailed analytical modeling and test range measurements. Projectile/bullet path analysis is of great use to shooters because it allows them to establish ballistic tables that will predict how much vertical elevation and horizontal deflection corrections must be applied to the sight line for shots at various known distances. The most detailed ballistic tables are developed for long-range artillery and are based on 6-degree of freedom trajectory analysis, which accounts for aerodynamic behavior along the 3 axial directions: elevation, range, and deflection, and the 3 rotational directions: pitch, yaw, and spin. For small arms applications, trajectory modeling can often be simplified to calculations involving only 4 of these degrees of freedom, lumping the effects of pitch, yaw, and spin into the effect of a yaw of repose to account for trajectory deflection. Once detailed range tables are established, shooters can relatively quickly adjust sights based on the range to target, wind, air temperature and humidity, and other geometric considerations, such as terrain elevation differences. Projectile path values are determined by both the sight height, or the distance of the line of sight above the bore center line, and the range at which the sights are zeroed, which in turn determines the elevation angle. A projectile following a ballistic trajectory has both forward and vertical motion. Forward motion is slowed due to air resistance, and in point mass modeling the vertical motion is dependent on a combination of the elevation angle and gravity. Initially, the projectile is rising with respect to the line of sight or the horizontal sighting plane. The projectile eventually reaches its apex, highest point in the trajectory parabola, where the vertical speed component decays to 0 under the effect of gravity, and then begins to descend, eventually impacting the Earth. The farther the distance to the intended target, the greater the elevation angle and the higher the apex. The projectile path crosses the horizontal sighting plane 2 times. The point closest to the gun occurs while the bullet is climbing through the line of sight and is called the near zero. The second point occurs as the projectile is descending through the line of sight. It is called the far zero and defines the current sight and distance for the gun. Projectile path is described numerically as distances above or below the horizontal sighting plane at various points along the trajectory. This is in contrast to projectile drop, which is referenced to the plane containing the line of departure regardless of the elevation angle. Since each of these two parameters uses a different reference datum, significant confusion can result because even though a projectile is tracking well below the line of departure, it can still be gaining actual and significant height with respect to the line of sight as well as the surface of the earth in the case of a horizontal or near horizontal shot taken over flat terrain. Maximum point-blank range and battle zero. Knowledge of the projectile drop and path has some practical uses to shooters even if it does not describe the actual trajectory of the projectile. For example, if the vertical projectile position over a certain range reaches within the vertical height of the target area the shooter wants to hit, the point of aim does not necessarily need to be adjusted over that range. The projectile is considered to have a sufficiently flat point-blank range trajectory for that particular target. Also known as battle zero, maximum point-blank range is also of importance to the military. Soldiers are instructed to fire at any target within this range by simply placing their weapons sights on the center of mass of the enemy target. Any errors in range estimation are tactically irrelevant, as a well-aimed shot will hit the torso of the enemy soldier. The current trend for elevated sights and higher velocity cartridges in assault rifles is in part due to a desire to extend the maximum point-blank range, which makes the rifle easier to use. Drag resistance. Mathematical models, such as computational fluid dynamics, are used for calculating the effects of drag or air resistance. They are quite complex and not yet completely reliable, but research is ongoing. The most reliable method, therefore, of establishing the necessary projectile aerodynamic properties to properly describe flight trajectories is by empirical measurement. Fixed drag curve models generated for standard-shaped projectiles. Use of ballistics tables or ballistics software based on the Mayevsky/Sciacci method and G1 drag model, introduced in 1881, are the most common method used to work with external ballistics. Projectiles are described by a ballistic coefficient, or BC, which combines the air resistance of the bullet shape, the drag coefficient, and its sectional density, a function of mass and bullet diameter. The deceleration due to drag that a projectile with mass m, velocity v, and diameter d will experience is proportional to 1/bc, 1/m, v superscript 2 and d superscript 2. The bc gives the ratio of ballistic efficiency compared to the standard G1 projectile, which is a fictitious projectile with a flat base, a length of 3.28 calibers/diameters, and a 2 calibers/diameters radius tangential curve for the point. The G1 standard projectile originates from the C standard reference projectile defined by the German steel, ammunition, and armaments manufacturer Krupp in 1881. The G1 model standard projectile has a BC of 1. The French Gavre Commission decided to use this projectile as their first reference projectile, giving the G1 name. Sporting bullets, with a caliber D ranging from 0.177 to 0.50 inches, 4.50 to 12.7 mm, have G1 BCs in the range 0.12 to slightly over 1.00, with 1.00 being the most aerodynamic, and 0.12 being the least. Very low drag bullets with BCs greater than or equal to 1.10 can be designed and produced on CNC precision lathes out of monometal rods, but they often have to be fired from custom-made full-bore rifles with special barrels. Sectional density is a very important aspect of a projectile or bullet, and is for a round projectile like a bullet the ratio of frontal surface area, half the bullet diameter squared, times pi, to bullet mass. Since, for a given bullet shape, frontal surface increases as the square of the caliber, and mass increases as the cube of the diameter, then sectional density grows linearly with bore diameter. Since BC combines shape and sectional density, a half-scale model of the G1 projectile will have a BC of 0.5, and a quarter-scale model will have a BC of 0.25. Since different projectile shapes will respond differently to changes in velocity, particularly between supersonic and subsonic velocities, a BC provided by a bullet manufacturer will be an average BC that represents the common range of velocities for that bullet. For rifle bullets, this will probably be a supersonic velocity. For pistol bullets it will probably be subsonic. For projectiles that travel through the supersonic, transonic, and subsonic flight regimes, BC is not well approximated by a single constant, but is considered to be a function BC, m, of the Mach number m. Here m equals the projectile velocity divided by the speed of sound. During the flight of the projectile the m will decrease, and therefore, in most cases, the BC will also decrease. Most ballistic tables or software takes for granted that one specific drag function correctly describes the drag and hence the flight characteristics of a bullet related to its ballistics coefficient. Those models do not differentiate between wadcutter, flat-based, Spitzer, boat tail, very low drag, etc. bullet types or shapes. They assume one invariable drag function as indicated by the published BC. Several drag curve models optimized for several standard projectile shapes are however available. The resulting fixed drag curve models for several standard projectile shapes or types are referred to as the G1 or Ingalls, flat base with 2 caliber, blunt, nose ogive, by far the most popular. G2, Aberdeen J projectile. G5, short 7.5 degrees boat tail, 6.19 calibers long tangent ogive. G6, flat base, 6 calibers long secant ogive. G7, long 7.5 degrees boat tail, 10 calibers tangent ogive, preferred by some manufacturers for very low drag bullets. G8, flat base, 10 calibers long secant ogive. GL, blunt lead nose. How different speed regimes affect .338 caliber rifle bullets can be seen in the .338 Lapua Magnum product brochure, which states Doppler radar established G1 BC data. The reason for publishing data like in this brochure is that the Syachi/Mayevsky G1 model cannot be tuned for the drag behavior of a specific projectile whose shape significantly deviates from the used reference projectile shape. Some ballistic software designers, who based their programs on the Syachi/Mayevsky G1 model, give the user the possibility to enter several different G1 BC constants for different speed regimes to calculate ballistic predictions that closer match a bullet's flight behavior at longer ranges compared to calculations that use only one BC constant. The above example illustrates the central problem fixed drag curve models have. These models will only yield satisfactory accurate predictions as long as the projectile of interest has the same shape as the reference projectile or a shape that closely resembles the reference projectile. Any deviation from the reference projectile shape will result in less accurate predictions. How much a projectile deviates from the applied reference projectile is mathematically expressed by the form factor, I. The form factor can be used to compare the drag experienced by a projectile of interest to the drag experienced by the employed reference projectile at a given velocity, range. The problem that the actual drag curve of a projectile can significantly deviate from the fixed drag curve of any employed reference projectile systematically limits the traditional drag resistance modeling approach. The relative simplicity, however, makes that it can be explained to and understood by the general shooting public and hence is also popular amongst ballistic software prediction developers and bullet manufacturers that want to market their products. More advanced drag models. Custom drag models. Custom drag models, CDMs, for bullets are a more refined way of modeling drag for bullets because you're not referencing a standard like G1 or G7. Rather you're using the actual measured drag of a specific bullet in a ballistic solver. Seeing a need for accurate modeling of ballistics into extreme ranges, and the limitations of current systems, Brian Litz from Applied Ballistics decided to use the actual flight data from the Applied Ballistics state-of-the-art laboratory. This results in more accurate trajectory predictions, especially through transonic. Currently the most accurate method outside of 6DOF. Instead of using methods such as G1 or G7 where the bullet is compared against a standard or trying to use analytical methods which need to be corrected for, you can simply use the actual drag data of the specific bullet in question. This removes the need for things like segmented BCS, and complex corrective formulas like chord lines. To explain the problem being solved by CDMs, the simplicity of the standard curve approach is offset by the compromise that the actual unique projectile drag is not accurately being modeled for each and every bullet shape. Some bullets do not follow the G1 or G7 standard very well, which brings up a third problem. But this is easily solved by using a CDM instead of BC compared against a standard. CDMs dispense with the compromise of matching G standards and basically makes every bullet its own standard by modeling its unique drag. By using the bullet's own drag as tested in flight, custom drag models can model a bullet's flight through subsonic flight accurately. This is most important in the transition through transonic flight into subsonic flight, where many bullets perform very differently. The use of CDMs was made possible with today's computational power, even that found in a modern-day cell phone. This provides the most accurate, user-friendly, method for calculating firing solutions at extreme long-range distances with unrivaled accuracy. Only point mass solvers are capable of accurately modeling CDMs and the precision needed for ELR shooting. While different methods of solving for the math do exist, such as mathematical functions found in PEGSA, which simply approximates the curves, they still have the problem of following a table/curve. Using these methods it is not possible the true drag of a bullet like a custom drag model does. In order to fully understand how aerodynamics are modeled, and how custom drag models have given us the ability to extend our shooting ability to a mile and beyond, here is an article on the very subject, Aerodynamic Drag Modeling for Ballistics. Custom drag models were used when for the first time ever in competition a target was hit at a distance of 2 miles or further. This was done twice, at 2 different events to prove repeatability, creating a first in history where a ballistic solver was coupled with small arms fire to provide results at 2 miles. The first time being at the World's Longest Shot Challenge in 2017, the second time being at the King of 2 Miles 2017 when the Applied Ballistics ELR team became the first team in the history of KO2M to hit a 2-mile target in competition and the first time to hit 2-mile targets in back-to-back competition. PEGSA model. Another attempt at building a ballistic calculator is the model presented in 1980 by Drive Arthur J. PEGSA. Mr. PEGSA claims on his website that his method was consistently capable of predicting supersonic rifle bullet trajectories within 2.5 mm, 0.1 in, and bullet velocities within 0.3 m/s, 1 foot/s, out to 914 m, 1000 yd, in theory. The PEGSA model is a closed-form solution. The PEGSA model can predict a projectile within a given flight regime, for example the supersonic flight regime, with only 2 velocity measurements, a distance between said velocity measurements, and a slope or deceleration constant factor. The model allows the drag curve to change slopes, true/calibrate, or curvature at 3 different points. Downrange velocity measurement data can be provided around key inflection points, allowing for more accurate calculations of the projectile retardation rate, very similar to a Mach VSCD table. The PEGSA model allows the slope factor to be tuned to account for subtle differences in the retardation rate of different bullet shapes and sizes. It ranges from 0.1, flat nose bullets, to 0.9, very low drag bullets. If this slope or deceleration constant factor is unknown, a default value of 0.5 is used. With the help of test firing measurements, the slope constant for a particular bullet/rifle system/shooter combination can be determined. These test firings should preferably be executed at 60% and for extreme long-range ballistic predictions also at 80% to 90% of the supersonic range of the projectiles of interest, staying away from erratic transonic effects. With this, the PEGSA model can easily be tuned. A practical downside of the PEGSA model is that accurate projectile-specific downrange velocity measurements to provide these better predictions cannot be easily performed by the vast majority of shooting enthusiasts. An average retardation coefficient can be calculated for any given slope constant factor if velocity data points are known and distance between said velocity measurements is known. Obviously this is true only within the same flight regime. With velocity actual speed is meant, as velocity is a vector quantity and speed is the magnitude of the velocity vector. Because the power function does not have constant curvature, a simple chord average cannot be used. The Pejsa model uses a weighted average retardation coefficient weighted at 0.25 range. The closer velocity is more heavily weighted. The retardation coefficient is measured in feet whereas range is measured in yards, hence 0.25 *3.0 equals 0.75, in some places 0.8 rather than 0.75 is used. The 0.8 comes from rounding in order to allow easy entry on hand calculators. Since the Pejsa model does not use a simple chord weighted average, two velocity measurements are used to find the chord average retardation coefficient at midrange between the two velocity measurements points, limiting it to short-range accuracy. In order to find the starting retardation coefficient, Dr. Pejsa provides two separate equations in his two books. The first involves the power function. The second equation is identical to the one used to find the weighted average at r/4, at n*r/2, where r is the range in feet to the chord average retardation coefficient at midrange and where n is the slope constant factor. After the starting retardation coefficient is found, the opposite procedure is used in order to find the weighted average at r/4, the starting retardation coefficient minus n*r/4. In other words, n is used as the slope of the chord line. Dr. Pejsa states that he expanded his drop formula in a power series in order to prove that the weighted average retardation coefficient at r/4 was a good approximation. For this, Dr. Pejsa compared the power series expansion of his drop formula to some other unnamed drop formula's power expansion to reach his conclusions. The fourth term in both power series matched when the retardation coefficient at 0.25 range was used in Pejsa's drop formula. The fourth term was also the first term to use n. The higher terms involving n were insignificant and disappeared at n equals 0.36, which according to Dr. Pejsa was a lucky coincidence, making for an exceedingly accurate linear approximation, especially for ns around 0.36. If a retardation coefficient function is used, exact average values for any n can be obtained because from calculus it is trivial to find the average of any integrable function. Dr. Pejsa states that the retardation coefficient can be modeled by c*Vn, where c is a fitting coefficient which disappears during the derivation of the drop formula and n the slope constant factor. The retardation coefficient equals the velocity squared divided by the retardation rate a. Using an average retardation coefficient allows the Pejsa model to be a closed-form expression within a given flight regime. In order to allow the use of a G1 ballistic coefficient rather than velocity data, Dr. Pejsa provided two reference drag curves. The first reference drag curve is based purely on the Sciachi/Mayevsky retardation rate function. The second reference drag curve is adjusted to equal the Sciachi/Mayevsky retardation rate function at a projectile velocity of 2600 fps, 792.5 m/s. Using a .3006 Springfield cartridge, ball, caliber .30 square meters, 152 grains, 9.8 grams, rifle Spitzer bullet with a slope or deceleration constant factor of 0.5 in the supersonic flight regime. In other flight regimes, the second Pejsa reference drag curve model uses slope constant factors of 0.0 or -4.0. These deceleration constant factors can be verified by backing out Pejsa's formulas. The drag curve segments fits the form v(2, n/c and the retardation coefficient curve segments fits the form v2/v(2, n/c equals c*Vn, where c is a fitting coefficient. The empirical test data Pejsa used to determine the exact shape of his chosen reference drag curve and predefined mathematical function that returns the retardation coefficient at a given Mach number was provided by the U.S. military for the cartridge, ball, caliber .30 square meters bullet. The calculation of the retardation coefficient function also involves air density, which Pejsa did not mention explicitly. The Syachi/Mayevsky G1 model uses the following deceleration parametrization: 60 degrees Fahrenheit, 30 nhg and 67% humidity, air density ρ equals 1.2209 kg/m3. Dr. Pejsa suggests using the second drag curve because the Syachi/Mayevsky G1 drag curve does not provide a good fit for modern Spitzer bullets. To obtain relevant retardation coefficients for optimal long-range modeling, Dr. Pejsa suggested using accurate projectile-specific downrange velocity measurement data for a particular projectile to empirically derive the average retardation coefficient rather than using a reference drag curve-derived average retardation coefficient. Further, he suggested using ammunition with reduced propellant loads to empirically test actual projectile flight behavior at lower velocities. When working with reduced propellant loads, utmost care must be taken to avoid dangerous or catastrophic conditions, detonations, which can occur when firing experimental loads in firearms. Measuses model. Although not as well known as the Pejsa model, an additional alternative ballistic model was presented in 1989 by Colonel Duff Measuses, U.S. Army retired, at the American Defense Preparedness, ADPA, 11th International Ballistic Symposium held at the Brussels Congress Center, Brussels, Belgium, May 9–11, 1989. A paper titled Closed-Form Trajectory Solutions for Direct Fire Weapons Systems appears in the Proceedings, Volume 1, Propulsion Dynamics, Launch Dynamics, Flight Dynamics, pages 665 to 674. Originally conceived to model projectile drag for 120 mm tank gun ammunition, the novel drag coefficient formula has been applied subsequently to ballistic trajectories of center-fired rifle ammunition with results comparable to those claimed for the Pejsa model. The Measuses model uses a first principles theoretical approach that eschews G-curves and ballistic coefficients based on the standard G1 and other similarity curves. The theoretical description has three main parts. The first is to develop and solve a formulation of the two-dimensional differential equations of motion governing flat trajectories of point mass projectiles by defining mathematically a set of quadratures that permit closed for.
Please subscribe and thanks for watching.